We can't start filling the lake.
But the dam is just part of the project. Before they can generate power, workers must blast a giant turbine hall out of solid rock and dig a tunnel 40 kilometers long. For 4 years, the construction team will toil in the harsh Icelandic wilderness to get this high-voltage megastructure powered up and producing electricity. They'll face equipment failure,
What happened?
rockfalls, and flooding.
Miserable working conditions.
In a battle against time to build the Icelandic super dam. Iceland, August 2006. For over 3 years, work has been underway on the country's biggest ever engineering project, the Karanuka Dam. The goal of this massive venture is to harness the power of one of Iceland's most abundant resources, water, and turn it into cheap electricity.
Basically, this project is very sound for our economy. We have very few resources in this country. We can not only live on fish exports. One of the main resources we have is water power and geothermal power. And so we are harnessing both.
A hydroelectric project like this requires the building of not one, but 3 enormous structures. A dam, 13 times the size of Wembley Stadium, to harness and collect water from 2 raging glacial rivers. A massive piping system, almost as long as the Channel Tunnel, to deliver a high-pressure torrent of water from the dam to the final stage of the project, the powerhouse, a hydroelectric generator plant, housed in a cavern blasted from solid rock a kilometer inside a mountain. The challenges are enormous.
It's a battle with nature, of course. Underground, it's a battle with the rock and the inflow of groundwater. On the surface, it's a battle with the elements.
This is a critical stage of the build. In just 5 weeks, the dam must be ready to collect water, and a major section of the tunnel has to be completed. But this isolated and harsh environment will present the international team of engineers and builders with setback after setback. Everybody knows that a dam blocks rivers. But to provide a dry working area while the dam is being built, the rivers must be diverted around the construction site.
When you build dams across a river course, the river has to be someplace during that construction period.
Diverting the 2 rivers here took 9 months alone. These rivers are central to the project, providing the water that will form a reservoir behind the dam, the water which will eventually power the turbines. And they're born here, at Vatnajökull, the largest glacier in Europe. Its ice cap covers over 7,700 square kilometers and contains around 3,400 trillion liters of frozen water. That's enough to cover the Isle of Wight with a block of ice 112 kilometers high. In summer, the glacier melts, creating a raging river system. But even with this powerful summer meltwater, the reservoir that'll be created behind the dam is so large that it'll take a year to fill. That's why the dam must be finished by September 2006. It's the only way they'll have enough time to fill the reservoir by autumn 2007, when power production must start.
Filling of a reservoir is always important in a project like this.
There is a big pressure to finish and start production and produce money.
If they miss the September deadline, not enough water will be in the reservoir next year to drive the generators and produce electricity. So time is tight. This type of dam is made by placing millions of tons of rubble into a gorge, then coating the outside of the rubble pile with concrete to make it watertight. And the best way to get the rubble is by blasting.
There's 2 main quarries on the site. Probably 80% of the dam materials come from this quarry.
On an average day, huge dump trucks drop 55 tons of rock and earth every 2 minutes. To improve waterproofing, rock is deposited in layers, from coarse to fine.
We're up to about 98% completion on the filling. So what you can see here, this last section of the dam here will be finished in the next month and a half.
Building a dam on this scale is an incredible feat of engineering. The pressure from 2,100 billion litres of water on the dam wall is huge. And it's this concrete covering that'll take the brunt of the force. To provide a strong foundation for the concrete covering, the workers first attach steel reinforcement, called rebar. The steep and slippery wall is exposed to strong winds blowing off the glacier. Working conditions are tough. One slip could end in a very long fall.
It's a very steep slope. The dam is about 200 meters high. So you always have to be careful on a construction site like this, yes.
The next stage is to cover the rebar in concrete. But there's a problem. At the on-site concrete factory, engineers have discovered there's too much air in the concrete mix. Get the mix wrong, and the concrete could crack, potentially disastrous in a dam.
Quality of the concrete has to be very good, otherwise you will have leakage through the dam, and it could be a disaster.
Has this been all night?
For Chief Engineer Richard Graham, the hold-up is very bad news.
And what are we doing to change it? What are the plant people doing? Sorry? I don't know.
Delays like this are a constant challenge on such a huge project, but they need to find a solution fast.
Can we put a new one? Can we go find a different batch, a new batch, completely new batch? We can't continue like this. We have all this concrete to throw away.
Dam construction is stalled until the concrete problem is solved. And there are only 5 weeks left until the dam must be ready to collect water. The Karanuka Dam project in Iceland. Autumn 2006. There's now only 1 month left to complete the dam in time to allow the glacial meltwater to form a reservoir.
To fill the reservoir, it takes more than a year, so it's that big.
If they miss their September deadline, the project will be massively delayed.
We could lose 1 season, and that could then mean a delay in the production and delivery of power for up to 1 year.
But nothing on this project is easy. Today's problem, a bad batch of concrete.
They're all bad. So what is happening now?
Too much air in the concrete mix means it can't be used, and work on the dam face is halted. Workers battle to resolve the problem. And eventually, they succeed.
All the concrete which is produced is tested. We had some values which were slightly higher than the ones planned in the design. So we had to readjust the dosage system and just put it back to what it should have been.
Every day, or at least every week, there is some difficulties that are arising, and it's a very tough thing to build a hydroelectric plant. Technically and construction-wise, it is complicated because there are so many different elements.
A new batch of concrete is rushed into production, and the workers can resume coating the dam face. The dam requires 450,000 tons of concrete to cover its face. And that massive amount has to be laid as a single, perfectly smooth layer. Any imperfections and the dam could leak. But how do you lay concrete on a surface sloped like a mountain? There's only one machine able to perform this gravity-defying stunt, and it's called a slip form.
The slip form is a structure which needs to be custom made on every single dam of this type, because you need to take into account the slope in which you're going to concrete the face slab. You need to take into account the width of the slate slab, plus also the length of the pores that you're going to perform.
It's pulled up the slope, or face slab, by 2 winches, whilst being fed with truckloads of wet concrete.
This slip form basically gives the constant thickness to be placed, and also the finishing of the face slab itself.
Workers standing on a platform inside the slip form smooth out any imperfections on the face. But once in motion, this giant machine can't stop. If it did, the face slab wouldn't be flawless, and there would be a danger of cracks. So the machine works night and day, covering a strip 60 meters long in one continual pour. With the slip form back up and running, the project's in full flow. The workers are happy. But not everyone in Iceland feels the same way. During the build, there's been some opposition to the dam from Icelanders. The project has left a massive footprint. 57 square kilometers of Iceland's pristine highlands lost underwater. The impact on wildlife is a concern. The reservoir side covers the breeding grounds of birds and reindeer.
I have all along kept in mind, why are we building this big project in the first place? For who is that good? And is it right to do it? And my conclusion has always been, yes, it is.
The majority of the power created by the project is for a new aluminium smelting plant. But any surplus energy can be fed into the national grid.
It is built for economical reasons. Electrical energy is getting, as everybody knows, more and more valuable in the world. In Iceland we produce what is regarded as clean energy. The rivers continue to flow, but we needed to make some compromises, of course, with the people.
Opinion is still divided. But despite the politics, this project is mind-boggling as an example of man's power to harness natural resources, and utilizes the one resource Iceland has in abundance: water. This is how it works. Water from two rivers is collected into a reservoir behind the dam. This water then travels along a huge pipe called the head race tunnel to the top of a mountain, where it's dropped 137 stories straight down. Flowing at 144,000 litres a second, this water then has enough power to drive 6 massive turbines, which generate huge amounts of electricity. To get the maximum power from the system, the reservoir must be as high as possible, and the powerhouse, where the turbines are, should be as low as possible.
The idea is to bring water from a higher place to a lower place, and the difference between elevations or heights is pressure, and it is the pressure that turns the turbines. But to get from the high point to the low point, in our case, is quite a sizable distance. 40 kilometers is the main tunnel. Even for most projects I've heard of, this is really on the high side.
Constructing the 40-kilometer tunnel required to get the water from the dam to the powerhouse is one of the biggest challenges on this project. Diverting huge amounts of water this far underground has never been attempted before in Iceland. It's an enormous challenge in the toughest terrain.
Even if we have excellent geologists, they can never predict fully how things look at 200 meters depth. It is unavoidable that there are always some surprises.
And to tunnel underground through the complex Icelandic geology, you need something rather special. This is a TBM, or tunnel boring machine. Weighing in at a monstrous 600 tons and measuring over 120 meters from tip to tail, this massive machine is designed for one thing only: eating rock. At the front, the cutter head is 7.5 meters in diameter, covered in hardened steel cutters. This is the business end of the beast, and where the tunnel borer attacks the rock face. Sitting behind the cutter head is the drive train. It gives the TBM the stability and power needed to crush solid rock to dust. Hydraulic legs and side grippers work together to stop the machine from spinning on its axis. 4 massive pistons provide the force to thrust the cutter head into the rock face. The crushed rock is then transported down the inside of the machine on a conveyor belt to keep the tunnel clear. Inside the TBM, it's cramped. There are workshops, storage areas, power and water supplies. Everything needed to support the lives of the 30 contractors who work there. It's an awesome machine, and the Karanjuka Dam project needs 3 of them. To cut construction time, the 3 TBMs work on different parts of the tunnel simultaneously 24 hours a day, 7 days a week. The first TBM cuts south. The second and third machines go east-west. And all of them are aiming to meet each other at predetermined locations in the tunnel. This is harder than it sounds, because underground there's no normal way of knowing which direction the machines are going. This far down, all reference to direction is lost. GPS, or global positioning systems, don't work. If they go off course, there'll be 3 separate tunnels going nowhere.
The tunnels have to meet, of course, to get the water through.
The job of making sure the TBMs go exactly where they're supposed to is down to the surveyors. Starting from a single known point, they use lasers to establish the exact location of the TBMs as they progress. The data is analyzed back at main camp to check if the TBMs are steering true, both horizontally and vertically. Using this information and a full array of computers and TV monitors on board, the drivers are able to steer the machines with incredible accuracy. The surveyors have tracked the TBM's path twice a day, every day, for over 2 years. Soon they'll find out if their calculations are correct. The tunnel borers are racing against the clock. The hydroelectric system has to be producing power by the autumn of 2007. To stay on schedule, the first TBM has to break through into the tunnel already bored by the second TBM by September 2006. If all goes according to plan, this meeting will take place here, halfway along the head race tunnel, in less than 1 month's time.
The challenges are always the same, that is to do the work in time. Well, my job is to push everybody, the designer, the contractors and the supervision. And on a huge project like this, you know, the time schedule is of essence.
This is tunneling on a time limit. If they can hit their deadlines, the water delivered by the tunnel will eventually arrive here, the powerhouse. This is where water will be turned into electricity. It's taken 3 years to carve this gigantic cavern out of solid rock. 340,000 cubic meters of rock have been cleared from inside the mountain. And the best way to clear a space this big is blasting.
Okay. Go.
Blasting is used for any excavations that are either too big or too small for the tunnel boring machine. But blasting above ground is dangerous enough. 180 meters underground, each detonation is a calculated gamble.
This is a dangerous job. You have to have the right equipment and the right people, experienced people. That's always the same.
There's a set pattern to this work. The area is cleared. The charge master primes his explosives, and everyone in the vicinity blocks their ears, closes their eyes, and braces for the blast. The shock wave surges up and down the confined space. The smoke clears, and success. A giant pile of rubble is all that's left of over 530 tons of wall, the weight of over 3 jumbo jets. That's a lot of rock, and it all has to be cleared. First, it's fed into a machine that crunches it into smaller pieces. This material is then fine enough to fit onto an industrial-sized conveyor belt, which is around 40 kilometers long. It's one of the most vital machines employed on this project. Without it, the tunnel would quickly become blocked. It's situated next to a subterranean railway, which carries a small army of men up and down the tunnels.
Our trains here are the only railway system that there is in Iceland. About 60 kilometers of rails to be able to reach all the excavation points inside the tunnel. Sometimes we had rides of 50 minutes. You can take a nap or a small rest.
High above the powerhouse, workers are constructing the pressure shafts. These are giant 420-meter vertical pipes that the water will plunge down before arriving at the turbines. But in order to drive the turbines, this water will be under huge pressure. And handling that bone-crushing force is no easy task. To prevent the high-pressure water from bursting out, the pressure shafts are reinforced with massive steel pipe.
Each piece is about 40 tons, lowered by heavy winch, put into place on top of the one below.
It takes precise and careful maneuvering to guide a pipe that big into place. Next, workers carefully weld the sections together.
It's a really tough job, I would say. It's hot in there, and this is not a job for anyone.
Water will enter the powerhouse at 144,000 litres per second. A system failure anywhere in the pressure shaft would flood the powerhouse in seconds.
It would be a disaster for the powerhouse. The powerhouse would definitely be flooded, and that would be a big economic disaster. But that isn't going to happen.
All the pipes in this system have to be immensely strong to cope with the high-pressure water they carry. It's the most unforgiving of adversaries. But the structure which has the toughest job with water is the dam. Stopping 2,100 billion litres of water from flowing away down the valley demands incredible planning and a highly skilled and conscientious workforce.
The dam itself has to hold a huge amount of water and huge pressures.
It's normal for dams to shift and settle over time, due to the huge weight of the rock they're made from and the immense water pressure of the reservoir. If it settles properly, a dam will be strong. If it doesn't, the constant pressure of the water will force it to give way. To ensure that the Karanuka Dam isn't moving too much or in the wrong way, surveyors mark positions on the face and then plot them against fixed coordinates.
Okay, Carlo, up 10 centimeters. Go up, go up.
They can then measure in what direction and by how far the wall is moving.
It continues to settle over time, and it is important to keep this within certain limits.
It's vital to monitor the behavior of the dam during the construction period.
Like a hole in a dike, even a small weak spot could bring the dam down. And for a structure this big, it would be a disaster on an unimaginable scale. In 2006, Brazil's Campos Novos Dam, the third tallest of its kind in the world, suffered a major failure. Billions of gallons drained from the reservoir, causing a massive disaster. So in Iceland, the surveyors monitor construction at every stage, checking for movement. At 200 meters high, the dam is the tallest of its kind in Europe.